Hi, I'm Grant Hocking with GeoSierra, and we're going to talk to you very briefly in this video about our technology of preventing liquefaction, that's soil liquefaction during an earthquake. Now, in order for us to quantify directly that your site is applicable for this technology, we developed this tool. Here we have our in situ tool, which measures directly the tendency for a soil to liquefy. Now, why we spent all this effort in developing this device was the current state of practice is to measure liquefaction potential of a soil indirectly. And what they do is they push a probe and just measure the resistance as you're pushing this probe in the ground, and then relate that to visual observations of liquefaction on the surface. It's very empirical and wasn't sufficient for us to show that the electro-osmosis was applicable at a site. So what we did was develop this tool. And what happens during an earthquake is earthquake produces a P wave, which is the first arrival, which has no energy with it, and then you feel that one first, but it's very, very low energy. But the main energy comes in the shear wave, and that comes through the bedrock and then propagates upwards through the soil, and that's the one that causes the liquefaction. And that comes later, and that has all the energy with it. Now, what we did was look at what an upward propagating shear wave does to the soil. And what it does is it basically compresses and tensions the soil in this sort of motion as it's climbing up the soil column. So we developed this device to actually quantify directly what's going on in an earthquake. So it's got two bladders. This is actually just driven into the ground to a certain depth. It's got two bladders. This one will expand, and at the same time this one will contract. Now, what that does is put the soil under zero volume change. And while this one expands, this one contracts, then oppositely, then this one will now expand and this one contract. And it goes in a cycle motion. And that cycling of expansion and contraction causes what we call stress reversal. And that's what happens in an upward propagating shear wave. So this will excite the ground as if it was an upward propagating shear wave. Now, Sam is going to just run these, and so you watch these bladders. And this will happen in the field. This will be driven to a particular depth, and then at that horizon this one will be inflated, and this one and that's contracted. Inflated, contracted. So that's what happens, and this little small amount of motion is enough to liquefy this whole zone of sand here. So Sam is going to start opening and closing these bladders, simulating that upward propagating shear wave, and then we'll zoom in and watch this area around here, and you'll be able to see it liquefy. Okay, so why don't we, so here we are going to have these bladders opening and closing, and what you want to do is look into this area here and see what's going on. See the water starting to come to the surface already? So now the soil is basically liquefying. This is all just like water. So this soil is just dropping, and that's what happens in the field. It may not look that dramatic in this little test apparatus, but a building would have just fallen over in this case. And see how the soil's dropped from here down to there, and all this water is now on the surface. And you'll see little sand boils, I don't know if you can see them, little miniature sand boils around the places you see in an earthquake where you have a volcano and a sand boil. What this little apparatus does show you, though, is that this tool tests a fairly large zone of the soil, and so it's liquefying all this soil here. Now, what the tool is really for, though, is to quantify whether electro-osmosis will prevent liquefaction at your particular site. Now, as Casagrande showed, that you apply this DC voltage, it drives the water immediately from the positive to the negative electrode straight away. So it's an instantaneous reduction in pore water pressure. So what we do is got the tool driven at a certain depth, it's being contracting and expanding, simulating an upward propagating shear wave, trying to induce liquefaction, measure the pore pressure rise. Then we apply a DC voltage, which is between the two bladders, and measure its rate of dropping that pore pressure, reducing that pore pressure, and quantifying directly that electro-osmosis will prevent liquefaction at that site during an earthquake. And so the process is then repeated. This is driven further down, etc., to quantify explicitly at your site that electro-osmosis is applicable, and not relying on some prediction. And with this tool, there's no prediction involved. This tool will measure directly whether that site is applicable for this technology, and there's no guesswork. This quantifies directly. The electro-osmosis will work. And you look at all the work of Casa Grande over the last 50 years, electro-osmosis is a very, very powerful system to stabilize soils. The thing is that no one thought about using it for earthquakes, and there is certain soils that won't work in. It won't work in all soils. It won't work in the real coarse, clean sands for sure. But all the soils in the western United States are very silty and directly applicable for this technology.